Hi everyone, in this video I'm going to talk to you a little bit about making a 5-spot model, actually a 1/4 5-spot model in MATLAB. And actually we're going to do it with MRST, which stands for MATLAB Reservoir Simulation Toolbox. So first thing we need to do is to define the grid. Let's start. Uh, at first, we need to use the function card grid. Why we use this function? Because we want our structure, our model, to be a Cartesian grid. So we use this function to create it. The first argument of this function is the number of cells in each direction. To make it prettier, let's actually define the dimensions or the cells, the number of cells, before the second line using the function deal, nx, ny, and nz. Nx is the number of cells in the x direction, ny number of cells in the y direction, and nz is the number of cells in the z direction. So using the function deal, we want to have 30 cells in the x direction and 30 cells in the y direction and 10 cells in the z direction, and putting a semicolon at the end. So now I put these variables as the first argument of the function, and if I want to determine the length of the model in the x, y, or z direction, I can use the second argument. But I'm going to actually quit using the second argument, because if I do it, it will use actually these numbers to determine the length of our model. So the length of the model in the x direction will be 30 meters, in the y direction 30 meters, and in the z direction 10 meters. And I used meter because MRST uses SI units, not field units that we usually use in petroleum engineering. So now I need to actually let's start. Let me actually run this line. Go to the next line to see the result. The structure G. We have these fields. Actually each of these fields, some of these fields are structures, like the structure cells, and it has its own fields, num, which is the number of cells of the structure, and some other fields are here. And you also see some other fields which actually give us some of the properties of our grid. But now I need to get some more information about the structure by using the function compute geometry. So now it's time to use the function compute geometry, and the input argument is the structure G, which was previously defined here. Alright, so now I defined the grid structure. Now it's time to actually define the rock properties. To define the rock properties and determine how their permeability and porosity are, I use the function make rock and put it in the variable rock. make rock. Be careful to use capital letters, you know, here, G, G, and R. If you don't do that, you will get an error. Make rock. As the first argument, I have, the grid structure. Then I should define, or I should determine the amount of permeability, and I consider it to be 200 millidarcy. As I told you, MRST works in SI units, so if I only write 200, it will think that actually I've written 200 square meter, but actually I said it's 200 millidarcy. So to convert it to the unit that MRST works with, I have to use these functions, millidarcy, to actually this, if I write this, actually it will be converted to SI units. Alright, so that's it. And now it's time to specify the amount of porosity. And I consider it to be 25%. Alright, it's 25%, and now semicolon. Now I should calculate the transmissibilities, but in MRST we calculate the half transmissibilities. If you want to get more information about it, you can read the books that are related to it. Half transmissibility, and use the function compute trans, and as the first argument we write G, or the grid structure, and the second argument will be rock. Alright, so we defined the half transmissibilities. Now it's time to define the fluid properties. To do that, I need to use a function which is in MRST module at incomp. So I should call this module by writing this MRST module at incomp, and now use the function that I wanted to use. And actually I put the information in the variable fluid. The function is this: init single fluid. Now it's time to specify the properties of the fluid. The first argument, actually in this function I use key value pairs. One of the pairs that I need to use is the viscosity. I consider the fluid to be water, so now I read the key, which is mu viscosity, and the value is 1 centipoise. And now it's time to specify the density, or rho, which is about 100 kilograms per cubic meter. Alright. Now I defined the fluid properties. So now it's time to define the wells that I have in the structure, in the model. As I told you, we have a 1/4 5-spot model. So I need to have 2 wells in the model. Now it's time to define it. I used the function vertical well because I want to have 2 actually two vertical wells, so I need to use two of this function. Vertical well, the first variable is actually you know the well, or the well that is previously defined, but because I've not defined any well yet, I leave it empty. Now I write G, the grid structure, the rock properties, and now I should actually tell the software in what cells are we want to be completed. First of all, I need to determine the horizontal location of the well, and I want it to be in the cell 1 and 1 in the x direction and 1 in the y direction, and I want it to be completed from the first cell to the last cell in the vertical direction. Now I want to define how our well is being controlled. Type of the control, which is I want it to be rate, and now I want to define the value of the rate, 100 or 1000 meter cubic meter per day. Now I define the value. Let's go to the next line. Now it's time to define the composition. I want it to be a single fluid. And now defining the radius of the well, and it is about 0.1 meter. And now I can define, of course, these key value pairs don't have any order. You can write them in any order you want. Now I determine the name of the well, which will appear on the figure. Name injector. Alright, so here there is a problem. What's missing here? We need a comma here. Alright. Injector, we specify the name, and that's it. Let's define the next well. We use the same function because we want to have another vertical well, but because we have already defined another well, we put here the variable w. Alright, but because we didn't have any well defined before this function, before this line, we actually considered this empty. We left it empty. Alright, so w, g, rock, and now we define the horizontal location of the second well, or our producer, n, x, and y, and z. Actually we're going to determine the cells that we want our well to be completed in them. 1, 2, and z. Alright, and type the type of the control, bottom hole pressure, and the value of it. We want it to be 800 psi. 800 psi. All right, and let's go to the next line. Okay, and now determine the composition of actually the fluid, and I want it to be a single fluid. All right, and now the radius of the well, the same, 0.1, and the name of the well, producer. All right, that's it, putting a semicolon. So let's make sure that everything is correct. All right, so it looks like everything is correct. So let's go to the next thing we need to do. Now, I wanted to, consider the effect of gravity. So I write the function gravity on. Gravity on. In this way, we consider the effect of gravity. And now it's time to calculate, the pressures of the cells, or the flow rate that we have in each cell, and things like them, by using the function init state. Actually, we use this function to determine the initial conditions of our reservoir. The first input argument is G, the second input argument is W, and the third input argument is the initial pressure of our reservoir. And I consider it to be 3000 psi. All right, now it's time to calculate the pressures and the flow rates by using the function incomp TPFA 2-point flux approximation, the method that is used for the calculations, the MRST. And the first input argument is the state that we defined previously. The second input argument is G, the grid structure. The third is half transmissibilities, and then is the fluid that we defined, the fluid structure. Then we need to specify the wells that we defined as a key value pair. All right, so now we actually defined the state of our reservoir, and now it's time to actually plot the results. So let's see them. We use the function plot cell data to see the grid. All right, to see the cells of the grid. We can also use some other functions to see some other features of our grid, but I will tell you about them in the future. So let's use this function, plot cell data. The first input argument is the grid structure, and then I need to specify the data that I need to show on the faces, actually on the cells or faces of the grid. And I want it to be the pressures. So I get the output of the structure state dot pressure, and as the output is in SI units, but I want it to be actually in PSI. All right, I want it to be in PSI, so I convert it to PSI by using the function convert to, and I write PSI. All right, so that's it. So we use this function to see the result, actually see the grid structure. So let me run the script. So let's see what the problem is. Convert to. Oh, the n is missing. Convert. All right. Okay. Now you see a two-dimensional view of the grid structure. But so let me close this and see it in the three-dimensional view. All right. And also I can use axis type off to see it better, and actually let me modify the color of the cells by using the jet, and let me also see the color bar. Alright, so now you see the structure. As you see, most part of the reservoir has a pressure which is about 3000 psi. Here we have the injector. Here we have the injector. There we have the producer, and that's why you observe that the pressure around the injector has increased, and the pressure around the producer has decreased. You see the drawdown in this part of the reservoir. So it's awesome. Now you see the structure, but as you may have already noticed, we don't see any wells. We're only observing the cells, but the wells and their names have not been shown yet. So let me plot the wells as well. Plot well. We use this function to plot the wells that we have. As the first argument, we should write G, the grid structure, the well structure, and also we need to define each well separately, because we want them to have different colors and things like that. And now I can define the height, how much the well, I want the well to come above the top of the reservoir, 2 meters, and now I can define the color of the well because I want it, because W1 is the injector, I want it to be blue. Alright, great. Now let's plot the second well, the producer. height, I want it to be the same, and color be black. Great. Now I think we're done. That's it. Let me see the whole model. What happened? B. Unrecognized function or variable B. Why B is blue? What's the problem? Oh, actually I should put him here. Great. So let's run it. Now as you see, the wells have also appeared on our model, and the two that I wrote here determine actually the height of the well that has come above the top of the well, actually the top of the reservoir. Alright, and here I have the injector, and there we have the producer, and as you see the wells have appeared on our model. That's it. I think actually I did everything I wanted to show you, and that's it. Thank you very much, everybody. Hope you're having a great day and time.